Hello, and welcome to the Snoozy Scientist. I'm really glad you made it here tonight. Wherever you are on this vast and beautiful planet, this little pocket of calm was made just for you, a quiet space where science and stillness can rest side by side, carrying you gently towards sleep. Tonight, we're not drifting back millions of years, but billions into one of the strangest and most haunting transformations the Earth has ever endured. Scientists call it the Great Oxidation Event, and in many ways it was the first great apocalypse. It may surprise you to know that the air we breathe, the oxygen that fills our lungs every second, was once the most dangerous poison the planet had ever known. When it first escaped into the skies, it was not a gift, but a catastrophe. It suffocated nearly every form of life that had once thrived. Whole worlds of microbes vanished. The Great Oxidation was not just another chapter in Earth's story. It was a reset, the first time life nearly ended by the hand of life itself. This cataclysm also paved the way for everything that would follow: forests, oceans, animals, and eventually us. But why was oxygen, that we know today as the breath of life, once the deadliest force on the planet? Why was it so toxic to those who came before us? And how did the fragile survivors adapt to a world that seemed determined to erase them? Tonight, we'll drift into that ancient past to see how the world nearly suffocated under its own breath. If you're already settling into this peaceful moment, it would mean the world if you gave this video a gentle like, maybe even subscribed, if you'd like more sleepy science stories like this one. And if you'd be kind enough, let me know in the comments, where are you winding down from tonight, and what time is it there? I love seeing how far across the world these science stories travel. So now, take a slow breath, let your shoulders soften, and together, let's begin the story of the day. Oxygen almost killed everything. Billions of years ago, long before forests or rivers, before animals, or even the faintest hint of flowers, Earth was already alive. Yet it was not the kind of life we would recognize. The planet was wrapped in an atmosphere heavy with gases that would choke us instantly. Methane and carbon dioxide filled the air, creating a blanket that trapped heat close to the ground. There was no oxygen to breathe. To us, this would have been an utterly hostile world. But to the tiny forms of life that thrived then, it was a paradise. The skies above were a strange sight. Instead of the clear blue we know today, the heavens shimmered in shades of orange, painted by the thick haze of methane. The sun struggled to pierce through, casting a dim and filtered glow. Days would have seemed muted, the light hazy and strange, as if the whole planet existed under a veil. The air itself was dense and unwelcoming, far from the refreshing atmosphere we take for granted. Beneath those orange skies stretched vast oceans, but they too looked nothing like the familiar blue seas of our time. They were filled with dissolved iron, giving them a greenish tint that shimmered under the weak light. Imagine waves tinted green, rolling endlessly under a heavy sky. These waters were the cradle of early life, and their chemistry was as alien as the atmosphere above them. Along the shallow edges of these seas, mats of microbes clung to rocks and sediments, spreading slowly like carpets of unseen architects. These were not plants, and they had no leaves or stems. They were colonies of simple organisms, weaving together to form living films that undulated with the tides. To the human eye, they might have seemed unimpressive, little more than slimy layers across the stone, yet they were the rulers of this world, quietly shaping the planet with their presence. The Earth's landscapes would have looked barren to us. There were no trees to break the wind, no grass to sway in the air, no flowers or animals to bring movement. Volcanic activity was common, sending plumes of smoke into the orange sky and spilling rivers of molten rock across the land. Mountains of stone jutted sharply, carved not by rivers or glaciers, but by tectonic upheavals. It was a raw planet, untamed and unfamiliar. Yet within the seas and shallows, life was steadily finding its way. In these early ages, the balance of the atmosphere was delicate. The methane-rich air created a greenhouse effect that kept the planet warm enough for liquid water to remain. Without it, Earth might have frozen solid under the faint young sun. The carbon dioxide that swirled through the sky was not yet the threat we think of today. Instead, it was a vital part of maintaining the fragile conditions that allowed microbial colonies to persist. Though the air was poisonous to us, the microbial world thrived. They absorbed the minerals around them, exchanged gases with the waters, and multiplied across the planet in numbers we cannot begin to imagine. These organisms were simple in structure, lacking the complexity of later life, but their influence on Earth would become profound. In time, they would change not only their own environment, but the destiny of every living thing that would follow. To walk through this ancient landscape in our imagination is to enter a place both eerie and majestic. Picture a coastline bathed in dim orange light, the sea lapping against bare rock, its waters green with iron. Above, the air is thick and heavy, a world of methane and haze. There is no sound of birds, no hum of insects, only the hiss of volcanic gases and the soft rhythm of waves. Yet within that silence, unseen to any eye, life stirs in abundance. This was the stage upon which one of the most dramatic transformations in Earth's history was about to unfold. From these microbial mats and green seas, a quiet revolution was beginning. Tiny organisms had learned a new trick, one that would unleash a gas no world had yet known, a gas that would turn the orange skies blue and the green oceans red and bring both death and possibility to a fragile young planet. Within those strange green seas, life was already busy experimenting. For billions of years, the Earth had been ruled by simple organisms that survived by absorbing chemicals directly from their environment. They drew their energy from the minerals around them, from hydrogen, from sulfur, and from other chemical pathways that required no sunlight and no oxygen. It was a hidden world of quiet survival, tucked away in the folds of rock and tide. But eventually, something remarkable appeared, something so small it could barely be seen, and yet powerful enough to alter the destiny of the entire planet. These were the cyanobacteria. To the eye, they would have looked like little more than tiny blue-green specks, clinging together in colonies that spread across the shallow waters. They formed slippery mats on the seafloor and layered mounds that rose slowly, stone upon stone, building structures known today as stromatolites. Their appearance gave no clue to the secret they carried inside them, but within their microscopic cells, they held a recipe for transformation. Cyanobacteria were among the first organisms to master the process we call photosynthesis. Unlike the other microbes around them, which relied on chemical reactions in the dark, cyanobacteria learned to use sunlight itself as a source of energy. With delicate molecules arranged inside their cells, they captured photons streaming down from the sky and turned that light into food. From the simplest ingredients, water and carbon dioxide, they built sugars that allowed them to grow and spread. It was an elegant invention. Sunlight was everywhere, falling across the seas each day, steady and free. By tapping into it, cyanobacteria unlocked a near limitless supply of energy. With each cycle of light and dark, they grew stronger, weaving their mats more widely across the shallows and multiplying in numbers that seemed endless. But photosynthesis came with a byproduct, something released into the world that no other living thing had ever had to face. Each time cyanobacteria split water molecules and rearranged atoms to build their food, they let go of oxygen. To them it was waste, as harmless and invisible as steam. To everything else alive at the time, it was a stranger, an alien gas with the power to destroy. At first, there was no danger. The oceans eagerly soaked up this new gas, dissolved iron within the waters bound to it, creating rust that sank silently to the sea floor. For countless years, the oceans acted as a great sponge, capturing nearly every breath of oxygen before it could escape. Cyanobacteria flourished in this balance, spreading and expanding while their waste product disappeared into the chemistry of the sea. Yet over time, the balance began to shift. The oceans filled with more and more oxygen until their iron sinks were exhausted. The water could hold no more, and when the seas were saturated, oxygen began to leak upward, out of the waves and into the air. What had once been trapped beneath the surface now rose into the skies. The microbes that filled the planet were not prepared for this. Oxygen was a reactive element, quick to bind and break, and it disrupted the delicate machinery of their cells. Proteins twisted and fell apart, membranes oxidized and failed. For organisms that had never known its presence, the sudden intrusion of oxygen was like an unseen fire, touching everything and sparing nothing. Cyanobacteria, without meaning to, had released a poison into their own world. Yet at the same time, they had invented the possibility of everything that would come later. Forests, animals, even the breath in our lungs, all trace back to this single innovation. They were both villains and heroes, destroyers and creators in one. The story of cyanobacteria is written in stone. Ancient stromatolites, layered like cakes of sediment and life, still stand in shallow waters today, their forms unchanged for billions of years. They are monuments to the moment when sunlight was captured for the first time, and when the fate of Earth turned in an unexpected direction. As oxygen continued to gather, the world began to change in ways that no microbe could have imagined. Oceans that had once gleamed green with dissolved iron would soon shift in color. The very chemistry of the seas was preparing to transform, and with it, the stage of life itself. Once the first whispers of oxygen began to escape from the work of the cyanobacteria, they entered a world not yet ready for them. The seas of that time were saturated with dissolved iron, far more than any ocean of today could hold. Each molecule of oxygen that drifted into the water instantly met this iron, and the reaction between them was both quiet and world-changing. In this slow but relentless process, the iron lost its old form. Bound tightly with oxygen, it became rust. Imagine entire oceans behaving like a vast cauldron, each drop of water meeting the new gas and rusting silently from within. What began as invisible chemistry soon became visible on a planetary scale. The seas, once green with their load of dissolved metals, began to take on a different hue. They darkened, then shifted toward a reddish tint, as though Earth's waters themselves were bleeding. It is difficult to picture oceans stretching from horizon to horizon, stained with the colors of oxidation. The waves no longer sparkled with life-giving green light, but rippled in shades of rust. For millions of years, these reactions continued, layer upon layer of iron particles sinking down through the water and collecting on the sea floor. Each particle was a fragment of oxygen's growing presence, a tiny record of the invisible storm that was reshaping the planet. These iron-rich layers built slowly into vast deposits, covering the ocean floors with stripes of red and gray. Over unimaginable spans of time, sediments pressed together, hardening into stone. Today we call them banded iron formations, and they can still be seen on every continent, some of the oldest rocks on Earth. In them, geologists read the signatures of this ancient transformation. Each band is a line in the diary of a planet learning to breathe. The sight would have been haunting, coastlines touched by waves that shimmered in rusty reds, waters carrying the burden of iron dying in oxidation. skies reflecting a dull glow above seas that no longer looked familiar. No single storm or eruption caused this shift, but a slow, persistent chemistry happening silently in every pool, every tide, every depth of water. These changes were not sudden to the organisms alive then. To them, the transition stretched across countless generations, far too slow to notice from one day to the next. But to us, looking back across billions of years, the scale of the transformation becomes clear. Oceans that once carried minerals in solution had been stripped bare. The vast reserves of dissolved iron that once painted the seas green were consumed, locked away forever in solid stone at the bottom of the deep. The minerals produced by this oxidation process shaped not only the color of the oceans, but the very foundation of the continents. Over time, as tectonic forces pushed and pulled, these rusted layers of stone were lifted upward. What had once been the floor of ancient seas now stands in cliffs and ridges. They are monuments to the day the oceans turned red. Some of the iron we use today in buildings, machines, and tools was born in that silent reaction between oxygen and seawater, a reminder that the Earth's deep past still touches our present lives. As the seas grew heavier with rust, the balance that had once contained oxygen within the waters began to fail. The sinks of iron could no longer absorb it all. The sponges of the ocean were saturated, and oxygen, for the first time, began to escape into the open air. The chemistry of the planet had reached a turning point, and what began with ripples of red in the sea would soon reach into the skies themselves. For a long time, the oceans had been able to contain the oxygen released by cyanobacteria, binding it to iron and drawing it down into the depths as layers of rust. But eventually, the balance could no longer hold. The iron was used up, the waters saturated, and the excess oxygen had nowhere left to go. Slowly, invisibly, it began to rise. What had once been a hidden reaction beneath the waves now drifted into the skies above. The atmosphere of early Earth was thick with methane. This gas had acted like a greenhouse blanket, trapping what little warmth came from the young and faint sun. Without it, the planet might have frozen into silence. Methane kept the world warm enough for liquid seas to spread across its surface, warm enough for microbial mats to cling to the shallows. Yet when oxygen escaped into the air, it found methane waiting. The two could not coexist peacefully. As oxygen increased, it tore apart the fragile bonds of methane. The greenhouse blanket that had wrapped the Earth for billions of years began to unravel. The protection that had held back the cold of space grew thinner and weaker. In time, the skies that had once glowed orange with haze cleared and sharpened, revealing new shades of blue. But this clarity came at a price. The planet itself began to shiver. Even more devastating was what oxygen meant to the life already present. For the organisms of that world, air had always been heavy with methane, carbon dioxide, and other gases that nourished them. They had evolved in the absence of oxygen, their delicate biochemistry shaped by a world that did not know this reactive gas. When oxygen touched them, it burned, not in flames, but in the quiet collapse of their cells. Proteins unraveled, membranes oxidized, and delicate molecular machinery corroded as if eaten from within. To those early organisms, oxygen was poison. Entire microbial populations fell silent, unable to adapt to the intrusion. Colonies that had thrived in the shallows withered and died. Biospheres that had stretched across the seas and coasts vanished in waves of invisible suffocation. The very air had turned against them, changing from a silent supporter into a lethal threat. In some places, the poisoning was swift. In others, it crept more slowly, as oxygen levels built over countless generations. But everywhere, the change was inescapable. The anaerobic life that had once ruled the earth was forced into retreat. Some escaped to the depths of the oceans, where oxygen could not easily penetrate. Others clung to the safety of sediments or volcanic vents, hiding in pockets where the old gases still lingered. Those that could not find such refuges were lost forever. The transformation of the atmosphere did not only suffocate life, it reshaped the world itself. With methane stripped away, the balance of heat on Earth tilted, less energy was trapped, and the surface cooled. In time, this cooling would lead to glaciations of unimaginable scale. But even in its earliest stages, the planet was no longer the same. What had once been a greenhouse world was shifting towards something colder, harsher, and stranger. The sight of the Earth in this moment would have been haunting. Skies once heavy with orange haze were clearing, revealing a sharper light, but the clarity hid the silent devastation happening all around. The seas, stripped of their protective chemistry, now fed oxygen upward into the skies. The air that had sustained microbial worlds became the very agent of their destruction. The planet was beginning to breathe, but in that first breath, it also began to choke. As oxygen continued to gather above, the pressure on life grew heavier. The fragile organisms that had once painted the world with microbial mats were pushed to the brink. Their reign, which had lasted for billions of years, was collapsing in the face of a gas that none of them had foreseen. And in this collapse, the first great extinction in Earth's history was beginning to unfold. As oxygen spread through the atmosphere, the impact on life was slow but merciless. Generations of microbes, each adapted to a world without oxygen, suddenly found themselves facing a gas that corroded the very chemistry of their cells. For billions of years, they had known stability, breathing in methane and carbon dioxide, thriving in waters rich with dissolved minerals. Then, without warning, their surroundings became hostile. It was not a single dramatic event, no sudden blow from the heavens, but an invisible change in the air and water that unfolded across countless ages, leaving devastation in its wake. Whole populations of anaerobic microbes began to collapse. Where once they had stretched across coastlines in endless mats, building living carpets in shallow seas, they now withered and vanished. Colonies that had covered stones and sediments turned pale and died away, unable to withstand the creeping presence of oxygen that spread like a silent tide. In deeper waters, too, the same story unfolded. Microbial communities that had endured for ages dissolved into nothingness, leaving behind only faint traces in sediments. It was the planet's first true mass extinction, though the life lost was too small for the naked eye to ever see. Entire biospheres that had flourished for eons were erased, the diversity of microbial forms cut down as if the Earth itself had swept them away. Some scientists suggest that as much as 90% of life disappeared during this time, though the record is too ancient to measure precisely. What is certain is that the balance of existence shifted sharply. The air and seas had become toxic to those who had once thrived in them. Oxygen, relentless in its reactivity, touched every surface, infiltrated every crevice, and altered every chemical bond it encountered. For the microbes that had no defense against it, there was no escape, no way to adapt in time. Their proteins unfolded, their cell membranes oxidized, their energy cycles failed. To them, the new atmosphere was not a gift, but a death sentence. Yet in the shadows of this catastrophe, there were survivors. Not all life vanished. Deep in the oceans, where oxygen could not easily penetrate, anaerobic communities found refuge. In the lightless regions near hydrothermal vents, microbes clung to volcanic gases, drawing their energy from sulfur and methane as they always had. In sediments buried beneath the seafloor, other pockets of life endured, hidden away from the rising tide of oxygen above. These were the remnants of a once dominant world, reduced to enclaves of survival. The earth had become divided. On the surface and in the upper layers of the seas, oxygen was spreading, turning the environment hostile to the old forms of life. Below, in the dark and the deep, the old world lingered, diminished but not entirely gone. This division would shape the course of life for all time to come. The scope of the extinction is almost impossible to imagine. For billions of years, anaerobic organisms had been the only form of life, shaping the chemistry of the planet in their slow and steady way. Their reign had lasted longer than any kingdom of plants or animals ever would. And yet, within a span that seems abrupt in the vastness of geologic time, their dominance ended. The old biospheres, rich and diverse in their microscopic way, vanished almost completely, leaving the Earth forever changed. Even today, echoes of those survivors remain, in places devoid of oxygen, buried in sediments or sealed within mineral layers. Microbes still live much as they once did. They are reminders of the ancient age before oxygen, carrying forward the memory of a time when the world was theirs alone. But on the surface, the balance had shifted. Oxygen was no longer just a trace element, no longer something swallowed by the seas. It was rising, spreading, and remaking the planet in ways no living thing could have foreseen. As the microbial worlds crumbled, the Earth itself began to change shape in response. The climate shifted, the chemistry of oceans transformed, and the very color of the skies evolved under the pressure of the new gas. In the wake of mass extinction, the stage was being set for something even more dramatic, a cooling so deep and far-reaching that the planet itself seemed to freeze. As oxygen spread through the air, it slowly dismantled the blanket of methane that had once wrapped the planet in warmth. For billions of years, that methane had acted as a greenhouse shield, trapping heat from a sunlight that was weaker than the one we know today. Without it, the Earth might never have been warm enough for liquid seas to endure. But oxygen tore methane apart, stripping away the fragile protection that had kept the world from freezing. The effect was not immediate, but across thousands and then millions of years, the temperature of the planet began to fall. The skies, once hazy and orange, grew clearer, but the clarity carried a chill. Clouds drifted over a cooling earth. The seas that had shimmered green and then red from chemical reactions now began to feel the touch of cold. Slowly, ice began to creep from the poles. What started as thin layers of frozen water at the edges of the world grew thicker and spread further. With less methane to hold in the heat, the cooling fed upon itself. Ice reflected sunlight back into space, preventing warmth from being absorbed at the surface. The more the planet froze, the more it continued to freeze. This self-reinforcing cycle pushed Earth into one of the most extreme states it would ever experience. According to the snowball Earth hypothesis, the freeze spread so far that glaciers eventually reached the equator. The tropics, which in later ages would cradle lush forests and teeming seas, became locked under sheets of ice. Imagine a world where every ocean surface is sealed with frozen crust, where mountain ranges vanish beneath glaciers that stretch for thousands of kilometers, and where the horizon gleams white in every direction. It was not simply a cold spell or an ice age like those in more recent history. It was a near-total freezing of the planet. For life, the challenge was nearly insurmountable. Microbes that had once covered shallow coastlines now faced a lid of ice blocking sunlight and trapping the seas beneath. With the surface sealed, photosynthetic organisms could no longer spread freely in the open water. The Earth had become a prison of frost, and survival was reduced to the narrowest margins. Yet even here, life endured. In the dark depths of the oceans, hydrothermal vents continued to pour out heat and nutrients. Around these volcanic openings, communities of microbes clustered, feeding not on light, but on the chemical energy erupting from the seafloor. Cracks in the ice, where shifting plates and restless geology fractured the frozen surface, also created small sanctuaries. Through these gaps, a little light still filtered down, just enough for pockets of photosynthesis to persist. It is thought that such refuges were all that kept the planet from falling silent. In these scattered havens, microbes continued their quiet work, clinging to existence against impossible odds. If not for them, the Great Oxidation might have ended not only with extinction, but with the complete erasure of life from Earth. The image of this frozen world is difficult to imagine. Oceans stretching white and solid to the horizon, ice kilometers thick, blanketing the continents. A silence across the surface where no rivers flowed, no rain fell, no waves broke upon the shore. Only deep beneath the ice did warmth and movement remain, in the unseen glow of volcanic vents and in the tiny cracks that linked the darkness to the pale light above. Over time, volcanic activity continued to release gases into the air, slowly adding carbon dioxide back into the atmosphere. With the greenhouse blanket rebuilt, Earth would eventually warm again, and the ice would retreat. But before that thaw, the planet lingered in this deep freeze for millions of years, testing the resilience of every living thing that remained. In the aftermath of suffocation and freezing, the world was reshaped once more. Oxygen still hovered above, gathering strength, while life below adapted to its new role as both a threat and a possibility. The survivors that clung to vents and cracks were all that remained of an ancient world, yet within them lay the seeds of everything yet to come. In the silence of a frozen planet, with oxygen rising above and seas sealed in ice, life did not disappear completely. Though most of the microbial world had collapsed under the suffocating touch of oxygen, pockets of survivors endured in places untouched by the poison. These were the anaerobes, organisms that had never needed oxygen and still could not tolerate it. They withdrew into the hidden places of Earth, slipping into the shadows to escape the new atmosphere that threatened their existence. Beneath the seafloor, in sediments packed with minerals and gases, these ancient forms of life found safety. The mud and stone protected them from the growing presence of oxygen in the upper waters. Here they continued their work in silence, living much as they had for billions of years, drawing their energy from chemical reactions instead of light. Their world was smaller now, cut off from the open seas, but they persisted. Some found refuge in the hot glow of hydrothermal vents, where volcanic energy poured out of the planet's crust. Around these vents, life could continue without the sunlight, relying on the chemicals that bubbled up from the deep. Sulfur-eating microbes flourished in these places, breaking down compounds that were toxic to many other organisms. They created energy by reshaping sulfur molecules, weaving survival from the minerals released by the Earth itself. Others clung to methane, producing it in dark places where oxygen could not follow. These methane producers, or methanogens, were relics of an older world. They thrived in environments that mirrored the conditions before oxygen arrived, transforming simple compounds into energy and releasing methane back into their tiny refuges. Though their numbers were far smaller than they had once been, they carried forward the memory of a time when methane had filled the skies. For life at the edge of extinction, every adaptation was vital. These microbes developed defenses against the faint traces of oxygen that sometimes seeped into their shelters. Some evolved enzymes to neutralize the damage. Others shifted their metabolisms to rely on compounds that remained stable in oxygen's presence. Though they could never dominate the planet again as they once had, they found ways to endure. The contrast between the poisoned surface and these hidden refuges could not have been greater. Above, the seas were stained with rust, the skies were filling with oxygen, and ice stretched across the continents. Below, in vents, sediments, and cracks in the crust, life clung stubbornly to the old ways, persisting in darkness and heat. This division carved a line through Earth's history, separating those who could endure oxygen from those who could not. In this period, the Earth became a place of dual worlds. On the one hand, oxygen was spreading, creating the conditions that would one day make complex life possible. On the other, ancient forms of life held tightly to existence in places that seemed hostile but were, for them, safe havens. The two worlds existed side by side, but only one would shape the future of the planet. The survival of these anaerobic microbes is not just a story of endurance, but also of diversity. Life has always found a way to adapt, to use the energy available in whatever form it appears. By feeding on sulfur, methane, or minerals buried deep in stone, these organisms proved that even in the harshest conditions, life could find footholds. Their quiet persistence ensured that the legacy of the pre-oxygen world would never be completely erased. Even today, their descendants remain in the depths of oceans, in swamps, and in places where oxygen cannot reach. Anaerobic microbes continue to live as they did billions of years ago. They are living fossils, reminders of the time when Earth's atmosphere was deadly to them, and yet their line endured through the greatest catastrophe the planet had ever known. While most of the microbial world was erased, these survivors were enough to carry life through the age of oxygen's rise. They endured in silence, waiting in hidden corners while the surface of the Earth transformed above them. Oxygen continued to spread, the skies continued to shift, and the planet itself kept evolving, setting the stage for the next great change that would sweep across the world. As oxygen continued to spread, its reach extended far beyond the seas and into the very air above. For countless ages, the atmosphere had been thick and murky, veiled in a haze of methane and carbon compounds. The sunlight that touched the earth was dim and filtered, casting the world in shades of orange and brown. It was a sky unlike anything we would recognize, heavy with the gases of a younger planet. But with oxygen rising, the haze that had blanketed the atmosphere began to thin. Molecule by molecule, oxygen broke apart the methane that had once dominated the air. What had been dense and hazy slowly gave way to something clearer. The sun, no longer muffled by layers of orange mist, began to shine more sharply. For the first time in Earth's long history, light scattered across an open sky. The scattering of shorter wavelengths, particularly blue, gave the heavens their familiar color. The planet that had always seemed alien was starting to resemble the world we know. The birth of blue skies marked a profound shift. From that moment onward, the Earth carried a face that future life would one day recognize. The air became transparent, revealing stars at night with new clarity and letting sunlight paint the day with brilliance. It was as if the planet had taken a deep breath and, in exhaling, transformed its appearance forever. Yet this new clarity carried the memory of catastrophe. Those blue skies were not merely symbols of openness and light, but also reminders of the worlds that had been lost. Countless microbes had suffocated as oxygen spread through their waters and air. Whole biospheres had collapsed in silence, their reign erased by a gas they could not endure. The blue sky was born of their absence, a canvas painted by extinction as much as by survival. For the survivors, The transformation was both a challenge and an opportunity. The transparent skies allowed more sunlight to reach the surface, creating new conditions for photosynthetic organisms. The filtered orange glow of the past was replaced by light that pierced more deeply into the seas, opening new niches for life that could use it. The world was no longer the dimly lit place of its early ages, but a brighter stage for what was yet to come. Imagine standing on the edge of one of those ancient coasts, though no human eye would ever witness it. Before you, the seas shimmer in their strange red tint, stained by the rust of iron dying in oxidation. Above, the sky stretches wide and blue for the very first time, a color that had never graced the world before. It would have been a sight both beautiful and unsettling, a landscape where death and rebirth existed side by side. The symbolism of those blue skies runs deep in the history of life. They were a signal that the old world had ended and a new one had begun. For the first time, the earth looked outward with an open atmosphere, clear enough to let sunlight and stars shine freely. It was a transformation not only of chemistry, but of perception, changing forever how the planet appeared from within and from afar. The same skies that became blue also gave rise to another crucial development. With oxygen high above, new reactions began to form another protective layer, one that would shield the surface from sunlight's most harmful rays. This shield, though still in its infancy during those early times, would open new possibilities for life. The planet, once suffocating and dim, was preparing itself for yet another stage in its story. With blue skies spreading above and oxygen filling the air, the earth had been transformed into a place of clarity and danger. For countless organisms, oxygen remained a poison, tearing apart their cells and forcing them into hiding. Yet within this hostile new world, some life found a way to do something extraordinary. They did not avoid oxygen, nor did they merely defend themselves against it. Instead, they learned to use it. This innovation was one of the most important in the history of life. It marked the birth of aerobic respiration, a process that would become the foundation for every plant, every animal, and every human who would ever exist. For the first time, oxygen was no longer a threat, but a tool. Before this, the energy that organisms could extract from their food was limited. Anaerobic respiration, the old way of breaking down sugars and compounds, produced only a small return. It was enough for microbes living in simple environments, but it placed a ceiling on how much energy life could command. When oxygen entered the picture, that ceiling shattered. Oxygen's chemical reactivity, once a danger, became the key to unlocking energy on a scale that had never been seen before. By using oxygen in their metabolic reactions, organisms could harvest many times more energy from the same food. A single molecule of sugar, once yielding only a faint trickle of energy, now released a flood when paired with oxygen. This surge of energy allowed cells to grow larger, to become more complex, and to support new structures within themselves. It was not simply survival anymore. It was expansion, innovation, and the opening of doors that had always been closed. The invention of breathing was not sudden. It took countless generations of trial and error, mutations and adaptations for cells to master the delicate balance of harnessing oxygen without letting it destroy them. They developed protective enzymes, molecules that neutralized the damaging byproducts of oxygen's reactions. They evolved systems to channel oxygen precisely, directing its energy toward useful processes rather than letting it run wild. Slowly, what had once been chaos became control. With this control, life tapped into a new powerhouse. Aerobic respiration became the ultimate strategy, offering efficiency that no other energy system could match. It was like trading a candle for a furnace, a dim spark for a roaring flame. The organisms that mastered it thrived, spreading across the seas and laying the foundation for the complexity that would follow. To imagine this shift is to picture the world not in terms of landscapes, but in terms of cells. Inside each tiny structure, invisible to the eye, energy was suddenly pouring in greater streams than ever before. Molecules raced through pathways, carrying power to build, to divide, to adapt. With every breath of oxygen, life found itself able to reach further. This change carried with it a new rhythm. Breathing was not yet the act of lungs or gills, but the chemical pulse of oxygen flowing into cells and fueling reactions. It was the quiet start of a process that would one day become the beating heart of animals, the rise and fall of chests, the constant tide of inhale and exhale. Every living thing that breathes today carries the inheritance of that ancient moment when oxygen turned from killer to savior. The transformation was not only biological, but ecological. Organisms that embraced oxygen began to reshape their environments, pushing out competitors that could not. The balance of power shifted, and the world tilted toward a new future. The survivors of the poisoned world, those who had clung to cracks and vents, still remained, but now a new form of life was taking hold, powered by the breath of the very skies. The invention of breathing was the bridge between a simple earth and a complex one. It provided the energy to sustain larger cells, to develop internal structures, and to form communities of cells that would eventually lead to multicellular life. Without it, forests would never have risen, animals would never have walked, and no human would have drawn their first breath. And as oxygen continued to spread across the planet, it was not only shaping the lives within the seas, but also leaving permanent marks in the very rocks of Earth, preserving a record of its arrival for all time. The story of oxygen's rise and the world it transformed is not just written in the memory of life, it is etched into the bones of the Earth itself. Long before humans walked the continents, the planet left behind its own diary, each page layered in stone, each line carrying whispers of the changes that swept across land and sea. To read these records is to step into the role of a time traveler, guided not by stories told, but by the silent testimony of rocks. One of the most striking of these records can be found in what geologists call banded iron formations. These are layers of stone, often striped in alternating shades of deep red and gray, that appear in ancient rock sequences across nearly every continent. They are the remnants of the time when oxygen first began to fill the oceans, binding with the dissolved iron and pulling it down to the seafloor. Each layer formed as waves of oxygen reacted with iron, creating vast blankets of rust that settled silently over the bottom of the seas. Imagine an ocean floor slowly painted in stripes. A pulse of oxygen sweeps through the waters, rusting the iron and laying down a blanket of red. Then, for a time, the oxygen fades, leaving behind darker layers of unoxidized sediment. Over millions of years, this pattern repeated again and again, building up bands that hardened into stone. Now, billions of years later, these bands stand as monuments to the rhythm of a planet in transition. The size of these deposits is almost beyond comprehension. Some stretch for hundreds of kilometers, forming ridges that tower above the land today. Much of the iron used in industry, the beams that hold up cities, and the steel that forges machines, was once part of these ancient layers. Every bridge and building that relies on iron carries within it the memory of a time when Earth's oceans turned red beneath the weight of oxygen. But banded iron formations are not the only witnesses. The geological record is filled with other markers that trace the rise of oxygen and the collapse of old biospheres. In layers of sediment, scientists find shifts in the chemistry of sulfur isotopes, subtle variations that reveal how oxygen began to dominate the atmosphere. In the oldest rocks, sulfur bears unusual patterns created in a world without oxygen. Above them, those patterns vanish, replaced by signatures that can only form when oxygen is present. It is as though the rocks themselves change their language, shifting from the script of an anoxic world to the script of a breathing one. Geologists treat these layers like pages in a vast, incomplete book. By drilling into ancient crust, by studying outcrops in deserts and mountains, they reconstruct the story written in stone. Dating these layers requires delicate work, using isotopes of elements like uranium and lead, which decay over billions of years with steady precision. Each measurement offers a timestamp, a way to mark when oxygen began to rise, when it surged, and when it faltered. The rocks also record the echoes of extinction. In places where microbial mats once thrived, stromatolites grew in great abundance. These layered structures, built slowly by cyanobacteria, appear less frequently after oxygen began to dominate. The decline of stromatolite formations preserved in stone mirrors the collapse of the microbial worlds that had ruled the planet for so long. Their scarcity in younger rocks is a reminder of the fragility of those ancient ecosystems. Standing before these ancient witnesses, scientists are reminded of the vastness of time. The bands of red and gray, the isotope shifts, the changing fossils of microbial life, all align to tell the same story. A story of oxygen rising quietly, invisibly, yet powerfully enough to remake the world. Without these stone records, the Great Oxidation Event would be little more than speculation. With them, it becomes one of the most certain and profound transformations in Earth's history. The testimony of the rocks does more than reveal the past. It opens doors to the chapters that followed. For as oxygen grew in the atmosphere, it began to assemble new molecules above, forming a shield that would change the relationship between the earth and sunlight and shape the next steps in life's unfolding journey. As oxygen gathered in the skies, its presence began to spark new reactions. High above the surface, where sunlight streamed unfiltered and intense, oxygen molecules drifted into the path of the sunlight's ultraviolet rays. These rays had always struck the earth without mercy, splitting apart molecules, altering chemical bonds, and making the upper atmosphere a place of constant disruption. But when oxygen entered this dance, something remarkable happened. Ultraviolet light was powerful enough to split oxygen into single atoms, and those atoms quickly sought to bond again. Sometimes they paired back into the simple form of O2, but often they joined in threes, forming O3, a molecule we know as ozone. One molecule of oxygen became two forms of itself, and in this transformation, the Earth gained something entirely new. Layer upon layer, ozone began to accumulate high above the surface. It was never thick, never visible, but it formed a shield of astonishing effectiveness. Ultraviolet radiation that had once blasted down to the planet's skin was now absorbed, intercepted by this fragile blanket. What had been a relentless storm of invisible light was softened and diminished. For the first time, the surface of the Earth was spared from the full force of the sunlight's most damaging rays. Before the ozone shield, life had been confined to hidden places. In the deep ocean, water acted as a natural filter, protecting microbes from ultraviolet radiation. In sediments and under stones, cells could survive without being shredded by the sunlight. The surface of the world, open and exposed, had been hostile, bathed in radiation strong enough to break DNA and unravel the molecules of life. But as the ozone formed, The danger lessened. The planet was beginning to create a protective canopy that opened new possibilities. This change did not happen overnight. The buildup of oxygen and its conversion into ozone unfolded over millions of years. Yet slowly, the balance shifted. More and more radiation was absorbed before it could reach the ground. The atmosphere itself had become a guardian, a filter that allowed the warmth and the visible sunlight to pass through, while blocking the invisible rays that had once scoured the planet. For life, the significance was profound. With the shield in place, organisms no longer had to remain hidden in the depths or buried beneath layers of rock and water. They could edge closer to the surface, exploring shallower waters where sunlight was abundant but less deadly. Photosynthetic organisms, already harnessing the power of light, found themselves able to expand into regions that had once been uninhabitable. The surface of seas and the upper layers of the ocean began to stir with new activity, shimmering with life that was no longer forced into hiding. The ozone layer also changed the very appearance of Earth. From space, the planet now reflected a balance of colors that signaled not only the presence of oxygen, but also the protective chemistry of ozone. It was an atmosphere that carried the fingerprints of life itself, a biosignature that today astronomers look for when scanning the skies for planets beyond our own. The shield that formed billions of years ago has become one of the markers we search for in distant worlds, hoping to find hints of life far away. The ozone shield was fragile, delicate, and dependent on the continuous presence of oxygen to sustain it. Yet it held, and by holding, it transformed the relationship between Earth and the sunlight. What had once been an environment of deadly exposure became one of potential. It was the beginning of a new chapter, where life was no longer bound only to the darkest depths or the safety of rock, but could start to venture upward, closer to the light. As the skies shifted and the shield strengthened, the story of the atmosphere continued to unfold. Oxygen levels did not remain steady. They rose, then fell, in waves that echoed across the ages, creating new challenges for life that was learning to adapt. The planet's atmosphere was not yet settled, but it was slowly moving toward a balance that would support greater complexity. The appearance of oxygen and the rise of an ozone shield did not bring immediate stability to the Earth. Instead, the planet entered into a long and uneasy struggle, a period where the atmosphere shifted like a restless tide. Oxygen levels did not rise in a straight line, but in waves. For millions of years, the air climbed toward abundance, only to fall again into scarcity, then rise once more. It was a world of fluctuation, a planet searching for equilibrium, yet never quite finding it. These swings were the product of a delicate balance. On one side, cyanobacteria continued to release oxygen through photosynthesis, spreading across the shallows and multiplying under the clearer skies. On the other side, the Earth's geology and chemistry worked to consume the gas as quickly as it formed. Volcanic eruptions spewed out reduced gases that reacted with oxygen and stripped it from the air. The weathering of rocks absorbed it too, binding it into minerals and pulling it out of circulation. For long stretches of time, oxygen built up only to be swallowed again by these hungry processes. The result was a planet caught in cycles of instability. At times, oxygen levels were high enough to transform the atmosphere, creating windows of expansion for life that had adapted to its presence. At other times, oxygen nearly vanished from the air, plunging the Earth back toward conditions closer to its ancient past. This push and pull lasted across millions of years, a slow rhythm of creation and erasure that shaped every living thing trying to survive within it. These fluctuations are preserved in the geological record. In some layers of rock, The chemical signatures point to a world rich in oxygen, while just above or below, other layers reveal conditions that were almost devoid of it. To study these rocks is to see the atmosphere breathing in slow motion, inhaling and exhaling oxygen across deep time. The bands of stone become a diary of the planet's struggle, each shift a record of its fragile attempt to balance competing forces. The effect on life was profound. Organisms that had begun to use oxygen for energy had to endure sudden declines, adapting to thinner supplies or retreating to niches where oxygen remained more stable. Those that still relied on oxygen-free environments found themselves expanding again during the crashes, only to be forced back into hiding when oxygen surged once more. The biosphere as a whole was stretched and tested, never able to settle fully, always adapting to a world in flux. The Earth itself seemed to waver between two identities. One was the older planet, wrapped in methane and carbon, where anaerobic microbes ruled and oxygen was scarce. The other was the emerging world of blue skies, ozone protection, and the possibility of more complex life. For millions of years, neither world fully won, and the Earth shifted uneasily between them. To imagine this age is to picture a planet that looked familiar but was not yet steady. The seas shimmered, the skies carried their new blue, and the ozone shield hung above, yet the very air was uncertain. It rose in strength, then weakened, as if the planet were still learning how to breathe. Each surge of oxygen promised stability, but each crash reminded life that nothing was guaranteed. Eventually, after these long cycles of rise and fall, the atmosphere began to settle. Oxygen no longer vanished completely. It became a permanent part of the air, though still subject to change. The instability did not disappear overnight, but the extremes softened. The planet was slowly bending toward a new balance, one where oxygen could remain in the skies, shaping the chemistry of the world and the future of life itself. Yet even as balance began to emerge, the fluctuating atmosphere left a legacy. It had tested the resilience of organisms, forcing them to adapt to scarcity and abundance alike. It had forged pathways for survival that would echo into the future, pushing evolution toward new forms and strategies. The story of oxygen was not yet finished, and as the atmosphere inched toward stability, life itself was preparing for the next great leap. As the atmosphere wavered between rises and crashes of oxygen, life faced a constant challenge. For many organisms, oxygen remained a threat, a gas that corroded their fragile chemistry and poisoned their cells. Yet, extinction was not the only path forward. Some microbes began to experiment with ways to endure. In their struggle for survival, they launched what could be called the first innovation race, a race not fought with weapons or speed, but with molecules crafted deep within their cells. Oxygen was dangerous because it was reactive. It sought to bond with whatever it touched, tearing apart delicate chains of proteins and damaging the vital machinery of life. When oxygen broke into unstable fragments called free radicals, it became even more destructive, burning through membranes and unraveling DNA. For microbes, every encounter with oxygen was like stepping into a storm that threatened to pull them apart. To face this storm, some developed defenses. One of the first strategies was the invention of antioxidants. These were molecules able to neutralize oxygen's harmful fragments before they could cause too much damage. Antioxidants acted like shields, absorbing the blows of reactive oxygen and turning chaos into stability. Within their cells, microbes that carried these protective molecules gained an edge, surviving longer than their vulnerable neighbors. Alongside antioxidants came enzymes, proteins with precise shapes and functions that could dismantle toxic oxygen byproducts. Catalase and superoxide dismutase enzymes still found in our own cells today, were among the earliest inventions of this age. They patrolled the interiors of microbial cells, breaking down reactive molecules into safer forms, such as water. These enzymes were not perfect, but they reduced the relentless damage and gave their hosts the time and stability needed to grow and reproduce. The microbes that carried these innovations became pioneers in a dangerous new world. Each small improvement in their chemistry meant more resilience. They could spread into areas where oxygen was present, gaining access to resources that had become closed to those who remained defenseless. The innovation race favored those who adapted fastest, pushing evolution forward in fits and starts. The story of this race is still written within us. Every breath we take carries oxygen into our bodies, and every cell we own contains enzymes and antioxidants to protect against the same dangers faced by those ancient microbes. The legacy of their struggle is alive in the chemistry that keeps us safe, in the molecules that sweep away the damage caused by oxygen's fiery touch. For early life, these adaptations were not only shields, but stepping stones. Once microbes could withstand oxygen without dying, they could begin to explore how to use it. Some of them went beyond defense, finding ways to harness oxygen's reactivity for energy. These were the first experiments in aerobic respiration, the powerful process that would later dominate the living world. But before life could learn to breathe, it first had to learn to survive. The innovation race was not swift. It played out over millions of years as random mutations gave rise to new tools and natural selection favored those who bore them. In shallow waters, in sediments, and in regions touched by oxygen, survival was determined by who could endure its stress. Those without protection vanished. Those with even the smallest advantage endured. It was a quiet competition, fought invisibly at the scale of molecules, yet its outcome shaped the future of the planet. With each step, life grew more resilient, more capable of withstanding the challenges of a changing Earth. The adaptations that began as desperate measures against a toxin would one day open the door to greater complexity, fueling larger cells and, eventually, multicellular life. But in this early stage, the struggle was still raw, a battle against invisible chemistry. Life's first innovation race was underway, and through it, the foundations of survival in an oxygen-rich world were being laid. And as this race unfolded in the seas, a new kind of cell was preparing to appear, one that would change the course of evolution forever. The long race to survive oxygen's presence pushed life toward new solutions, and eventually, a transformation unfolded that would redefine what a living cell could be. From the fragile simplicity of the first microbes arose a new kind of organism, one that carried within it an innovation so powerful it changed the destiny of the Earth. These were the eukaryotes, cells that were larger, more complex, and equipped with structures that allowed them to thrive in ways their ancestors never could. The turning point came with a partnership. At some stage in this deep past, a primitive cell engulfed another, not as food, but as a companion. The smaller cell was a bacterium, already skilled in the art of using oxygen to release energy. Instead of being digested, it was kept alive inside its host. This unlikely alliance became permanent, and over time, the two cells merged into a single organism. The smaller one evolved into what we now call the mitochondrion, the powerhouse within almost every eukaryotic cell alive today. This union was extraordinary. Alone, the host cell could survive only with limited energy, relying on slower, less efficient pathways to fuel itself. With its new partner inside, it could suddenly extract dozens of times more energy from the same food. Oxygen, once feared as a toxin, became the key to unlocking power on a scale never seen before. The mitochondrion carried out the dangerous chemistry of respiration in a controlled space, providing fuel while sparing the rest of the cell from oxygen's destructive force. The consequences of this partnership were immense. With abundant energy available, eukaryotic cells grew larger than their ancestors. They could afford to maintain intricate internal structures, separating different processes into compartments. They could support complex DNA molecules, allowing them to store far more genetic information than earlier cells. With more instructions coded into their genes, they could build proteins with new functions, branching into diverse forms that adapted to every corner of the environment. The cellular revolution was not only about survival, it was about possibility. These new cells could change shape, extend arms to capture food, and even begin to communicate chemically with one another. They were flexible in ways that prokaryotes, the older and simpler microbes, could never be. Each new layer of complexity was fueled by the steady flow of oxygen-powered energy delivered by their mitochondria. The rise of eukaryotes also transformed ecosystems. Where once the microbial world had been dominated by small, single cells competing in narrow niches, eukaryotes expanded into new spaces. They colonized shallower waters, soils, and sediments, growing in numbers and diversity. Their complexity made them versatile, able to adapt to shifting oxygen levels and changing climates. Slowly, they began to dominate the environments where survival had once been precarious. This revolution set the stage for everything that would follow. Without the abundant energy provided by mitochondria, multicellular life would have been impossible. The cooperation of many cells into tissues, organs, and entire organisms requires vast amounts of power, and only aerobic respiration could sustain it. The appearance of eukaryotes, born from the unlikely partnership of two cells, opened the door to forests, animals, and eventually human beings. To imagine this transformation is to picture not a single dramatic event, but countless tiny exchanges playing out over time. One cell taking another inside, mutations shaping their coexistence, generations passing until what began as a fragile arrangement became permanent. Each step was invisible to the eye, yet together they changed the course of evolution forever. The mitochondrion, once a free-living bacterium, became an inseparable part of the larger whole. Its descendants live in every one of our own cells, still producing energy in the same way as they did billions of years ago. Every heartbeat, every breath, every movement is powered by their ancient chemistry. The cellular revolution is not just history. It is ongoing, within us and within all complex life that inhabits the earth. With eukaryotes firmly established, the planet was ready for more. Oxygen had not only been tamed, but harnessed, and with this came the potential for organisms of greater size, diversity, and resilience. The rocks, too, continued to record these changes, capturing traces of the chemical world that shifted as oxygen carved itself deeper into the story of Earth. Even as new forms of life began to thrive with oxygen, the rocks of the Earth were silently keeping their record. Long before the first written language, before fossils of animals or leaves of plants, the chemistry of the planet itself was inscribing its history in stone. These inscriptions were not words or images, but patterns hidden in the atoms of sulfur, carbon, and iron. To geologists, they are as clear as a diary, revealing how the atmosphere shifted and how entire worlds of life were extinguished. One of the most telling signatures comes from sulfur. In the ancient atmosphere, before oxygen rose, ultraviolet sunlight reacted with sulfur gases in strange and unpredictable ways. These reactions left behind a fingerprint, tiny irregularities in the ratios of sulfur isotopes that became locked into rocks. For billions of years, these chemical quirks marked a world without oxygen. They appear in sediments from that early time, like notes scribbled across every continent. Then, suddenly in the geologic record, the signature vanishes. The irregular patterns disappear, replaced by a smoother balance. The reason lies in the chemistry of oxygen. Once oxygen filled the skies, it changed the rules. Ultraviolet light no longer split sulfur gases in the same wild manner because oxygen absorbed and scattered much of that radiation. From that point onward, sulfur isotopes settled into more predictable patterns. It was as if the rocks stopped speaking in one language and began speaking in another. The disappearance of these sulfur isotope anomalies is one of the clearest signs that oxygen had truly taken hold in the atmosphere. It is not a trace that can be seen with the naked eye, but one measured in laboratories with delicate instruments, comparing the weight of atoms locked in minerals. Layer after layer, the story emerges, an ancient Earth suffocating under methane and haze, then shifting into an oxygen-rich world that erased the old chemical rhythms forever. Other clues confirm this transformation. Carbon isotopes in certain layers suggest that vast amounts of organic matter were buried at the same time oxygen levels were climbing. Iron formations, already stained red from oxidation, appear in cycles that align with these atmospheric changes. Together, the rocks preserve a chemical archive of disaster, extinction, and rebirth. To imagine these stones is to picture cliffs and outcrops that seem ordinary to the eye, yet within them lie whispers from billions of years ago. In some of the oldest parts of Canada, South Africa, and Western Australia, geologists find these markers, the remnants of oceans that once shimmered green, then turned red, and finally gave way to skies of blue. Each rock carries within it a record of how oxygen rose like a tide, swallowing the old world and forcing life to adapt or perish. The rocks are not silent witnesses. They speak through their chemistry, telling us when oxygen first accumulated, how long it fluctuated, and how catastrophic its effects were. Without these signatures, the Great Oxidation might remain a vague theory. With them, it becomes undeniable, a story carved into the crust of the Earth itself. These chemical fingerprints reveal not only the rise of oxygen, but also the scale of extinction it caused. They show us how deeply the planet changed, how the very air was rewritten, and how entire ecosystems vanished. Each sulfur signature erased is a reminder of the worlds of microbes that suffocated as oxygen spread, their deaths recorded not in fossils, but in the shift of atoms within stone. And even as oxygen stabilized and eukaryotic cells began to flourish with their mitochondria, the rocks continued to bear witness. They became the bridge between biology and geology, carrying the memory of a time when life nearly ended, but also when new forms began to take hold. The planet's crust became a library of catastrophe, each page written in iron, sulfur, and carbon. As the atmosphere continued to evolve, the Earth itself was not finished with extremes. The rise of oxygen, combined with the fragility of the planet's balance, would bring about more episodes of freezing and thawing, locking the world in cycles of ice and survival. The chemical fingerprints locked in stone tell us not only of oxygen's arrival, but of the upheavals that followed. Among the most dramatic were the great freezes that swept across the planet. These events, now called snowball Earth episodes, seem to have returned again and again, each linked in part to surges of oxygen in the atmosphere. With every boom in oxygen, methane was stripped away, and with methane gone, the planet's greenhouse blanket grew thin. The Earth cooled, sunlight reflected from expanding sheets of ice, and soon the freeze fed upon itself. Glaciers advanced far beyond the poles, inching down through the continents. The oceans, once free and open, froze over with thick crusts of ice that stretched almost to the equator. It is difficult to imagine seas, thousands of kilometers wide, locked beneath unbroken ice, yet evidence suggests that the Earth may have been sealed in white more than once. These were not short-lived chills, but stretches of cold that lasted for millions of years, reshaping the planet's surface and testing the resilience of every living thing. For life, these freezes were both deadly and strangely protective. On the one hand, vast areas of the surface became uninhabitable. Photosynthetic organisms, once spread across sunlit shallows, were trapped under ice where light could not reach. Whole ecosystems collapsed as oxygen surged above and the seas froze below. To many microbes, this was another catastrophe, a narrowing of habitable space that forced them into retreat. Yet at the same time, the ice created sanctuaries. Though the surface was locked, beneath the frozen crust the oceans still flowed, insulated from the worst of the cold. In the depths, hydrothermal vents continued to pour out warmth and minerals, feeding communities that survived without sunlight. In cracks and thin spots where the ice fractured, some light could still filter through, enough for photosynthesis to continue in small, hidden patches. The very ice that killed so much life also preserved what remained, shielding it from radiation and stabilizing conditions below. In this way, the Earth became a paradox of survival. The freeze devastated ecosystems, but also acted as a protective shell. It narrowed life to the edges, to refuges along volcanic ridges and pockets beneath the ice, but those refuges endured. What might have seemed like the end of habitability instead became a bridge, carrying life across ages of cold until the planet warmed again. The geological evidence of these snowball Earth episodes can still be seen. Ancient glacial deposits appear in rocks near the equator, places that today are warm and tropical but once lay beneath walls of ice. These rocks bear scratches and striations from glaciers that slid over them, carving marks that still remain billions of years later. When paired with chemical evidence of oxygen booms, they tell a story of cycles, of freezing and thawing bound to the rise and fall of gases in the atmosphere. Imagine standing on such a frozen Earth, white stretches in every direction, continents buried under kilometers of ice, oceans sealed in silence. Above, the skies are crisp and blue, the air thinner of greenhouse gases than ever before. It would have been a world of stark beauty and haunting stillness, a planet that looked more like a frozen moon than the cradle of life. Yet hidden in that stillness, in cracks, vents, and deep currents, life was waiting. When volcanic activity eventually released enough carbon dioxide to rebuild the greenhouse effect, the ice began to melt. Slowly, the seas opened again, and the surface thawed. Each thaw marked not just the end of a snowball Earth, but the renewal of life's reach. Survivors spread once more, carrying with them the resilience forged in frozen exile. These periodic freezes remind us that oxygen was never a simple gift. It came in surges, each one powerful enough to drive the planet into extremes. The very gas that made complex life possible also threatened to erase it time and again. Yet through these cycles of death and refuge, life found ways to persist, clinging to the edges of a frozen Earth and enduring long enough for the next chapter to unfold. When the Earth finally emerged from its cycles of freezing and thawing, oxygen had secured its place in the atmosphere. The planet was no longer only a world of stone, ice, and water. It had become something more unusual, a world that breathed. Among the rocky planets of our solar system, this feature sets Earth apart. Oxygen fills our skies to levels that shape every living thing, from the smallest cells in the ocean to the tallest forests. Yet when we look outward to our neighbors, the contrast could not be sharper. Take Mars. Its skies are thin, its atmosphere little more than a faint whisper compared to Earth's dense cloak of air. The surface pressure is less than 1% of ours, and oxygen is almost absent. Instead, carbon dioxide dominates, making up nearly the entire atmosphere. Without oxygen, Mars has no blue skies. It is a dusty world of red deserts and frozen poles, cold and quiet, where the chemistry of breathing never had a chance to take hold. Then there is Venus, Earth's twin in size but not in spirit. Its atmosphere is suffocatingly thick, with carbon dioxide building a greenhouse effect so extreme that the surface is hot enough to melt lead. Clouds of sulfuric acid hang above its plains, and oxygen plays no role at all in its balance. On Venus, the air is not a giver of life but a smothering blanket of heat and poison. In this small neighborhood of rocky worlds, Earth alone carries oxygen in abundance. This makes our planet rare, at least in the places we can see nearby, and the reason is not chance. Oxygen at such levels does not appear on its own. It is too reactive, too eager to bond with rocks and minerals, to dissolve in oceans, or to vanish into chemical reactions. If left to itself, oxygen disappears. The only reason it lingers in our skies is because life constantly replenishes it. Every leaf, every cyanobacterium, every algae bloom adds to the supply, maintaining the balance that makes breathing possible. This connection between oxygen and life has become a guide for scientists searching beyond our solar system. When astronomers peer at distant stars and the planets that orbit them, they look for atmospheric fingerprints. By splitting starlight into spectra, they can detect the gases present in those alien skies. Among these gases, oxygen stands out. It is considered a biosignature, a potential sign that life may be at work. If we find a planet wrapped in oxygen-rich air, we suspect that something, somewhere on its surface or in its oceans, may be producing it. The search is cautious, because oxygen is not a guarantee. Geological processes can make small amounts, and unusual chemistry can mimic its presence. Yet the sheer abundance of oxygen we see on Earth is unlikely to be sustained without the constant work of living systems. It is the ongoing breath of the planet, the exhalation of forests, oceans, and microbial mats that keeps our skies filled. To imagine Earth as a breathing planet is to think of every inhale and exhale not just as a human act, but as a planetary one. The air we draw into our lungs is part of a cycle billions of years old, powered by photosynthesis and balanced by respiration. The world itself moves in rhythm, holding oxygen as both gift and burden, a gas that once nearly ended life and now sustains it. Looking outward, Mars and Venus remind us of what Earth might have been. One froze, the other burned, and both remain silent. Earth alone speaks with oxygen, its skies proclaiming that life is here. And as scientists trace light from distant exoplanets, they listen for that same message, hoping to find another world that breathes. From this broader view, oxygen is more than chemistry. It is a signal, a signature written in starlight, a quiet reminder that our planet carries something rare in the cosmos. But the same oxygen that marks Earth as unique also carries paradoxes of its own, shaping life while also challenging it at every step. Oxygen gave the Earth its breath and opened the door for complexity. Yet hidden within this gift lies a deep paradox. The very molecule that sustains us is also capable of undoing us. Life depends on oxygen, but too much of it, or oxygen left unchecked, becomes destructive. From the smallest microbe to the largest animal, every living thing walks this narrow line, balancing between oxygen as savior and oxygen as threat. The danger lies in oxygen's nature. It is restless, eager to bond with other atoms, quick to start reactions that spiral into chaos. This reactivity is what makes it so powerful inside our cells, allowing food to be broken down into energy. But the same property also makes oxygen difficult to control. When it interacts unpredictably, it creates unstable fragments called free radicals. These fragments are like sparks flying from a fire, capable of scorching whatever they touch. Even today, billions of years after the first microbes learned to live with oxygen, the risk remains. Every time we breathe, our cells are flooded with this reactive gas. Most of the time, enzymes and antioxidants keep it in check, guiding it through safe pathways. Yet some of it always slips away, sparking damage. This is oxidative stress, a slow process of wear and tear that erodes our cells over time. Proteins twist out of shape, DNA strands break, and membranes weaken under the strain. In humans, oxidative stress is linked to aging, wrinkles on the skin, the gradual decline of strength, even the slow loss of memory have connections to the invisible damage caused by oxygen. Diseases such as cancer, Alzheimer's, and heart conditions are also tied to this paradox, where the very gas that fuels life leaves behind traces of harm. Scientists still search for the full map of how oxygen shapes both vitality and decline, but one truth is clear: oxygen is not an unbroken gift. It is a double-edged presence, always demanding balance. For other organisms, the story is similar. Plants that release oxygen through photosynthesis also suffer from its effects within their own tissues. They too produce antioxidants and protective molecules to fight the stress. In the deep oceans, fish rely on oxygen dissolved in water, but sudden rises in oxygen levels can overwhelm them. Even the bacteria that first harnessed oxygen billions of years ago continue to maintain enzymes that guard against its destructive side. Across the tree of life, the same theme repeats. Oxygen is both essential and dangerous. The paradox becomes even sharper when viewed through time. At moments in Earth's history, oxygen levels rose higher than today, reaching levels of 30% or more in the atmosphere. During these times, wildfires became more common, ignited by sparks that would otherwise have fizzled. Insects grew to enormous sizes, their bodies supported by the abundance of oxygen, yet the world also grew more flammable, more volatile. Too much oxygen created a planet at risk of burning. Too little, and complex life could not survive. It is as though life has always been walking a tightrope, stretched across the deep ages of time. On one side lies suffocation, on the other lies destruction by excess. Every organism, from the first eukaryote to the humans breathing now, exists because the balance has been maintained. The earth breathes, but it must always breathe just enough, never too much. This fragile balance is maintained by cycles of life and geology working together. Forests and oceans produce oxygen, while respiration, decay, and volcanic gases consume it. The result is a planet that regulates itself, holding oxygen at levels that are high enough to sustain life, but low enough to prevent catastrophe. It is a balance that has wavered many times, but never broken completely. The paradox of oxygen reminds us that even the most familiar things can hold hidden dangers. Each breath carries the same contradiction. The molecule that powers our cells is also slowly wearing them down. Life continues not by eliminating the threat, but by living with it, adjusting and adapting across generations. Oxygen has never been fully tamed, only managed, and as this delicate balance played out across the Earth, the echoes of the Great Oxidation continued to ripple forward. The first mass extinction, the freezing of the seas, the rise of complex cells, and the slow dance between suffocation and fire all trace back to the moment oxygen took hold. The shadow of that ancient catastrophe has stretched across every age, shaping not only the past, but the future still to come. The paradox of oxygen reveals its sharpest edge when we step back and look at the history of extinctions on Earth. Across the past half-billion years, scientists speak of the Big Five, five catastrophic events that reshaped the course of evolution. Each was devastating in its own way, each marked by staggering losses. Yet when compared with the Great Oxidation Event, they seem like echoes of an earlier and even greater upheaval, a shadow that stretches back billions of years. The first of the Big Five came at the end of the Ordovician period, about 440 million years ago. Life was flourishing in the seas, but a sharp and sudden cooling, triggered by shifting climates, wiped out nearly 3/4 of marine species. Then, in the late Devonian, around 370 million years ago, ecosystems collapsed again, with reef builders and fish disappearing in waves. The third, the most infamous, came at the end of the Permian period, 252 million years ago. This great dying erased more than 90% of species, leaving the planet desolate before life began its long recovery. The fourth struck at the end of the Triassic, clearing the stage for dinosaurs to dominate. And the fifth, most familiar to us, ended the reign of those same dinosaurs when a great asteroid struck 66 million years ago, opening the way for mammals to rise. Each of these extinctions was catastrophic, reshaping the web of life in profound ways. Yet the Great Oxidation stands apart, because it did not simply eliminate species. It transformed the very conditions that made life possible. The Big Five were disasters imposed upon a living world that already knew oxygen, forests, and complex ecosystems. The Great Oxidation was different. It was not a single strike from an asteroid or a burst of volcanic fury. It was the slow reweaving of the planet's atmosphere, a shift in chemistry that altered every corner of the biosphere. It was less like a single catastrophe, and more like the rewriting of the rules of existence. The irony is haunting. Unlike later extinctions, which were driven by external forces, the Great Oxidation was caused by life itself. Tiny cyanobacteria, multiplying in shallow seas, released the oxygen that would poison nearly every other organism alive at the time. In their effort to grow and thrive, they produced the very gas that nearly ended the world around them. The first mass extinction in Earth's history was not caused by an asteroid or a supervolcano, but by the invisible breath of life itself. To imagine this is to confront a paradox as deep as oxygen itself. The same molecules that suffocated ancient anaerobes also paved the way for the rise of breathing, the evolution of eukaryotes, and eventually the emergence of animals and humans. Without the Great Oxidation, there would be no forests, no birdsong, no seas filled with whales. But with it came one of the most profound purges the Earth has ever endured, a near death that set the stage for every future form of life. In this way, the Great Oxidation casts a long shadow across all later extinctions. The Big Five rearranged life, but the Great Oxidation invented the possibility of rearrangement itself. It established oxygen as a permanent feature of the atmosphere, an element that could rise and fall but never disappear entirely. It created a planet where every subsequent extinction unfolded under its influence. Even the fires that raged in oxygen-rich ages, even the suffocation that followed oxygen crashes, all trace back to that first upheaval. The rocks that carry the signatures of sulfur and iron remind us that this was not a single event, but a turning point in Earth's history. The extinction it caused was more than a collapse of species. It was the creation of a new kind of planet. For the first time, Earth was no longer a world ruled by methane haze and iron seas. It had become a world of oxygen, fragile but enduring, a place where the very air could both kill and sustain. The Great Oxidation was not the largest in terms of percentage of species lost, nor the most sudden, but it was the most profound. It was life's own byproduct that nearly erased life itself, and in that irony lies one of the greatest stories of our planet. It shows us that catastrophe and creation are often intertwined, that survival can come only through transformation, and that the shadow of one ancient extinction still falls across every breath we take today. Even as oxygen reshaped the planet and swept away much of the ancient biosphere, life did not vanish completely. In the hidden corners of the earth, microbes continued to endure, not by breathing oxygen, but by crafting ingenious ways of drawing energy from the chemistry around them. These survivors were microbial alchemists, able to thrive in the shadow of oxygen by bending the elements of the earth into sources of life. Some became sulfur reducers, masters of a chemistry that seems almost alien to us. Deep in sediments and around hydrothermal vents, they fed on sulfur compounds, transforming them into simpler forms to capture energy. What was waste or poison to others became fuel to them. These microbes wove survival from the sharp scent of sulfur, crafting energy in the absence of oxygen and thriving in the very places where oxygen could not reach. Others turned to iron, feeding on the abundant metals scattered across the seafloor and buried within sediments. These iron eaters unlocked the energy hidden in rust, moving electrons between minerals in ways that powered their metabolism. To us, iron is the stuff of stone and steel, but to these microbes it was food, as essential as sunlight or air. Entire communities grew by passing electrons along chains of minerals, weaving invisible circuits through the rock. Still others clung to methane, producing and consuming it in delicate cycles that continued long after oxygen had claimed the skies. Methane producers, called methanogens, carried forward an ancient metabolism from the pre-oxygen world, releasing methane into the depths even as oxygen tried to erase it. On the other side, methane-consuming microbes fed on what was released, balancing the cycle. In these exchanges, they kept fragments of the old Earth alive, pockets of the methane-rich atmosphere preserved within the crust and the oceans. Together, these microbial alchemists formed a living mosaic of alternative metabolisms. Each one exploited a different chemical pathway, drawing from sulfur, iron, or methane to fuel their survival. They were not competitors so much as specialists, each occupying its own niche, each weaving a different thread of energy into the web of life. Their diversity was their strength, a strategy that ensured life could survive even when the world itself seemed to have turned hostile. The creativity of these microbes reveals something profound about life. It is not bound to a single way of drawing energy, nor limited to the familiar breath of oxygen. It is flexible, opportunistic, and endlessly inventive. Wherever there is a chemical imbalance, life finds a way to exploit it. The sulfur reducers, the iron eaters, and the methane clingers all stand as proof of this, reminders that survival often depends on turning the harshest conditions into hidden opportunities. The descendants of these ancient alchemists still exist today, quietly working in the background of our world. In deep ocean vents, sulfur-eating microbes continue to build ecosystems that flourish without sunlight. In soils and sediments, iron eaters still pass electrons through chains of minerals, invisible but vital to the cycles of the earth. In wetlands and the guts of animals, methanogens still produce methane as they did billions of years ago, linking us to the earliest chemistry of life. These survivors are not relics of a forgotten age, but living continuations of it. They are reminders that while oxygen came to dominate, it was never the only strategy, never the only path. Diversity allowed life to withstand catastrophe, to spread across niches and environments where no single solution could prevail. In this diversity lies resilience, the ability to endure upheaval and to shape new possibilities in the aftermath. As the Great Oxidation continued to ripple across the earth, these microbial alchemists remained as quiet counterpoints to the story of oxygen. While cyanobacteria filled the skies with breathable air and eukaryotes rose with mitochondria, the alchemists held on in the shadows, preserving the memory of older worlds and proving that survival can be written in many different chemistries. Their persistence ensured that even in catastrophe, the biosphere remained a patchwork of possibilities, and as the oxygen age deepened, the planet itself began to look more like the world we know. Blue skies and protective ozone stretched above, and the atmosphere leaned toward stability. Life, however, was still experimenting, still innovating, still reshaping itself in response to the new balance. The rise of oxygen did more than suffocate ancient life and leave chemical scars in the rocks. It acted as a reset button for the entire planet, clearing away the old and forcing life into new directions. For billions of years before oxygen, the biosphere had been a relatively stable place, dominated by microbes that lived in ways suited to a methane-rich, oxygen-free world. But with the Great Oxidation, stability gave way to disruption. Oxygen swept across the earth like an invisible tide, breaking apart the chemistry of the old ecosystems and leaving behind vast empty spaces. Extinction can seem like only loss, but in the history of life, it has also been the foundation for renewal. When one world ends, another begins, and the Great Oxidation was perhaps the most dramatic example. By erasing the dominance of anaerobes, oxygen opened ecological space for organisms that could endure or even thrive in its presence. The very catastrophe that threatened to erase life became the starting point for entirely new forms of survival. The reset was not a single event but a series of cascading changes. Each surge of oxygen rewrote the rules of chemistry and biology. Microbes that had once flourished across the oceans vanished, leaving room for cyanobacteria to spread even further. Eukaryotes, with their mitochondria, began to rise in prominence, powered by oxygen's energy-rich reactions. Even the planet itself bore the marks of reset, as rusted seas laid down, banded iron formations, and glaciers carved across continents during snowball earth freezes triggered by the loss of methane. This was not the first time the Earth would clear its stage, nor the last. Later extinctions, from the end of the Permian to the fall of the dinosaurs, all carried echoes of the same process. Old ecosystems collapsed, and new ones emerged to take their place. But the Great Oxidation was different because it changed the very medium of life. The air, the oceans, and the chemistry that every organism depended upon. It was not only a change of players, but a change of the game itself. To imagine this planetary reset is to picture silence sweeping across microbial mats that had thrived for eons, only for new voices to rise in their place. Where once the seas shimmered green with iron and life that shunned oxygen, new communities emerged, experimenting with respiration and learning to harness the gas that had destroyed their predecessors. The biosphere became a patchwork of innovation, filled with survivors who carried the genetic and chemical tools to live in a changed world. This pattern reveals something essential about the Earth. Catastrophe and creation are not opposites here, but partners. Each great disruption forces life to adapt, to transform, to push beyond what it was before. Without the reset of oxygen, life might have remained simple, microbial, and hidden, confined to the chemistry of an earlier planet. Instead, the upheaval cleared the path for complexity, for cells with nuclei, for multicellular organisms, and eventually for the vast ecosystems we know today. The idea of a planet reset also carries with it a sense of fragility. Oxygen was not inevitable. It was produced by tiny cells working slowly over millions of years, changing their world molecule by molecule. The catastrophe they unleashed could have erased life entirely, yet it instead became the foundation of everything that followed. The balance was delicate, a knife's edge between total destruction and renewal. Even now, the echoes of that reset remain. Every breath drawn today is part of a cycle that began in those ancient seas. Every forest, every coral reef, every field of grass traces its origin back to the moment when oxygen swept the earth and forced life to begin again. The reset was not a simple end. It was the great turning point that made a new kind of planet possible. And with oxygen established as a permanent part of the atmosphere, the stage was prepared for the next step, the blueprint that would allow life to grow more complex than ever before. With the Earth reset by oxygen, the conditions were set for life to attempt something it had never done before. For billions of years, organisms had remained small, single cells surviving in relative simplicity. They grew, divided, and adapted, but they did so alone, each cell carrying all it needed within its tiny boundary. This way of life was effective in a world with little energy to spare. But with oxygen flowing steadily into the atmosphere and into the seas, the possibility of something greater began to open. Oxygen was not only a poison or a shield, it was also a source of power. By breaking down food with oxygen, cells could release far more energy than ever before. Instead of scraping by on the limited returns of anaerobic chemistry, they could suddenly access dozens of times more fuel from the same resources. That energy was not just a luxury. It was the foundation needed to build something larger, more intricate, and more enduring. Multicellularity is demanding. A cluster of cells living together must do more than simply exist side by side. They must communicate, share resources, and divide labor. Some cells must take on specialized roles, while others provide support. This level of coordination requires an enormous supply of energy. Without it, the system collapses back into the simplicity of single-celled life. Oxygen provided the steady stream of fuel that made such cooperation possible. The blueprint for complexity was written in energy. With enough power, cells could afford to grow larger, to maintain internal structures, and to build networks with one another. They began to experiment with sticking together after division, forming filaments, sheets, or hollow spheres. Over time, these loose clusters gave rise to true multicellular organisms, where cells were no longer identical, but specialized into different roles. Some moved, some sensed, some protected, some fed the whole. This division of labor created bodies that were more than the sum of their parts. Plants, animals, fungi, and every complex organism trace their origin back to this turning point. Without oxygen, there would be no forest reaching toward the sky, no animals darting through seas, no wings cutting across the air. The energy demands of such complexity would have been impossible in an anoxic world. The Earth might have remained forever a microbial planet, its oceans filled with mats of single-celled organisms and nothing more. The rise of multicellularity was not immediate. It took millions upon millions of years of experimentation. Some early multicellular forms vanished without descendants, while others refined the art of living together. Yet the foundation remained the same: oxygen as the prerequisite, the fuel that kept the machinery of complexity running. It was as though the planet, once smothered in haze and rusted seas, had finally unlocked the instructions for building higher forms of life. Even within our own bodies, this blueprint is clear. Every breath we take brings oxygen into our lungs, and every cell in our body uses it to release energy from food. The patterns of cooperation between our trillions of cells are possible only because oxygen supplies the energy to keep them working together. The heartbeat, the movement of muscles, the firing of neurons in the brain all depend on the chemistry that first emerged when oxygen was tamed. To picture a world without oxygen is to imagine silence. No green of plants, no animals roaming, no humans wondering at their own history. The Earth would have remained strange and alien, its skies orange, its oceans green, and its biosphere locked in microbial simplicity. Oxygen did not just allow for change, it demanded it, pushing life into new forms and opening paths that would lead, in time, to every ecosystem and every species we know. And as oxygen secured its place in the atmosphere, it continued to flow through the cycles of Earth, carried by forests, oceans, and the very breath of living things. The blueprint it provided did not just shape the past, it remains active in every organism today, guiding the rhythms of life and sustaining the complexity that arose from a single invisible catastrophe long ago. The blueprint for complexity, etched into the chemistry of oxygen, did not remain a relic of the distant past. It continues even now, flowing through the rhythms of our living planet. Every breath of air we draw into our lungs is not only a reminder of ancient catastrophe, but also a part of a cycle that has never stopped turning. Oxygen is still being made, still being consumed, still shifting through forests, oceans, and the thin shell of atmosphere that cradles life on Earth. The great engines of this cycle are the forests and the seas. On land, forests stretch across continents, weaving themselves into the air with countless leaves. Each leaf is a solar collector, capturing the energy of sunlight and using it to split water molecules, releasing oxygen as a byproduct. From the tops of rainforests where canopies shimmer in green to the boreal forests of the north, where pines exhale their breath into cold skies, these living expanses maintain the balance of the air we depend upon. Yet it is not only the forests that carry this weight. The oceans, vast and deep, are perhaps the greatest lungs of all. Within their sunlit shallows, swarms of microscopic plankton perform the same task as the leaves of trees, photosynthesizing and releasing oxygen. Though tiny, these organisms are countless, and together they produce more than half of the oxygen that circulates in the atmosphere. With every gentle wave that ripples across the sea, the invisible breath of plankton rises, joining the balance that sustains life above and below. This cycling of oxygen is delicate, dependent on the cooperation of ecosystems that stretch across the globe. Oxygen produced by forests and plankton does not simply accumulate endlessly. It is consumed as well, drawn down by animals that breathe, by microbes that decay fallen leaves, by fires that burn, and by the steady processes of geology. The Earth breathes in and out, its atmosphere held in equilibrium by the balance of creation and consumption. The fragility of this balance becomes clear when it is disrupted. When forests are cut down or burned, their contribution to oxygen wanes, and the carbon they once stored is released back into the air. When oceans warm or acidify, plankton communities shift, altering the flow of oxygen they produce. Even the smallest changes ripple outward, reminding us that the air we take for granted depends on countless interlocking processes, each one vulnerable to change. The breath of the future is tied not only to the survival of forests and oceans, but also to the choices of species like ours. Humans shape the balance by how we use the land, how we burn fuels, and how we protect or neglect the systems that generate the oxygen we need. Though the atmosphere contains a vast store of oxygen, its renewal depends on living systems that are neither infinite nor indestructible. The story that began billions of years ago with cyanobacteria has reached a moment where its continuation depends on the guardianship of the very creatures it made possible. It is humbling to realize that the thin layer of breathable air around the earth is not guaranteed. It is maintained continuously, second by second, by the work of forests and seas. Every tree that grows, every wave stirred by the wind, contributes to a cycle as old as the planet itself. Without it, the atmosphere would slowly shift back toward a barren chemistry, a silent echo of the worlds of Mars and Venus. The future of this cycle lies in balance, just as it always has. The Earth breathes through its ecosystems, and we are woven into that breath. The same oxygen that once nearly erased life now sustains it, flowing through forests, oceans, and our own lungs. And as the atmosphere continues to pulse with this rhythm, the question becomes not whether oxygen will endure, but how life will continue to shape and be shaped by it in the ages to come. The Earth has always breathed in rhythms, its atmosphere rising and falling with the push of life and the pull of geology. Oxygen has surged in waves, at times flooding the skies, at times nearly vanishing, and always shaping the course of life. Today, the air feels steady, a familiar mix of nitrogen and oxygen that seems eternal, yet history whispers a different truth. The balance of oxygen is fragile, and it raises a haunting question. Could it happen again? Even in our own time, scientists detect fluctuations. The concentration of oxygen in the atmosphere has not remained fixed. It drifts downward slowly, measured not in sudden collapses, but in small decreases that accumulate over centuries. This decline is subtle, almost invisible to daily life, but it reminds us that the balance is not permanent. The reason lies in how oxygen is made and consumed. Forests, plankton, and other photosynthetic life add oxygen, while respiration, decay, and combustion take it away. When production falters or consumption rises, the scales shift. Human activity has become one of the strongest forces tilting those scales. By cutting down forests, we remove vast sources of oxygen. By burning fossil fuels, we not only consume oxygen, but also flood the atmosphere with carbon dioxide, altering the climate that supports the ecosystems making oxygen in the first place. In the oceans, warming waters and rising acidity disrupt plankton communities, weakening the lungs of the planet. Though the atmosphere still contains a massive reservoir of oxygen, its renewal depends on these living systems. If they collapse, the balance could falter more quickly than we imagine. The fragility of this balance is underscored by Earth's own history. During the Great Oxidation, life itself nearly ended by creating too much oxygen for the old world to endure. Later, surges of oxygen led to wildfire-prone ages, while crashes drove ecosystems into crisis. Each swing reshaped the biosphere. Today, The same cycles continue, but with an added pressure. Us. Humans have become a geological force capable of shifting atmospheric chemistry in decades rather than millennia. The possibility of a future oxygen crisis is not just a question of suffocation. A decline in oxygen could alter climates, ecosystems, and the chemistry of oceans. Even small changes could ripple outward, making survival harder for species finely tuned to the present balance. In some scenarios, scientists imagine a slow drift, where oxygen continues to decrease as forests are cleared and plankton diminish, leading to a planet that breathes less deeply with every passing century. The idea is unsettling, yet it also highlights how deeply connected we are to the atmosphere. Every tree, every wave stirred with plankton, every cycle of decay ties into the oxygen we breathe. The breath of the planet is not guaranteed, but continuously renewed through the cooperation of living systems. Disruptions to those systems remind us that the balance can be broken, that what feels stable is only stable because life holds it in place. Could another great oxidation type event unfold? Perhaps not in the same way, for the world is no longer filled with methane seas and iron oceans. But the principle remains. When the balance of gases shifts, the biosphere changes with it. What happened billions of years ago was life poisoning itself with oxygen. What happens now may be life endangering itself by consuming too much of it or by weakening the systems that sustain it. The irony remains the same. Life changes the air, and the air in turn reshapes life. The fragility of this truth is humbling. We breathe in confidence, but each breath depends on forests that can fall, on oceans that can warm, on cycles that can falter. The story of oxygen is not finished. It continues to unfold in the present moment, bound to the choices of a species capable of both destruction and care. As we study the fragile balance of oxygen on Earth, our gaze often turns outward to the stars and the planets that circle them. In the vast darkness of the universe, astronomers search for worlds that might resemble our own, places where life could take root. Among the many clues they look for, one stands above the rest: the presence of oxygen. Oxygen, by itself, is a peculiar gas. It is too reactive to linger in an atmosphere without something constantly replenishing it. Left alone, it bonds with rocks, dissolves into oceans, or vanishes into chemical reactions. A planet with abundant oxygen is almost certainly being reshaped by life, just as Earth has been for billions of years. To an astronomer studying distant light, oxygen becomes more than a molecule. It becomes a whisper of biology, a signature written across the skies of another world. The search for these signatures begins with starlight. As a planet passes in front of its star, some of the star's light filters through the planet's atmosphere. By splitting that light into a spectrum, astronomers can see the chemical fingerprints of gases swirling above the alien surface. Each gas absorbs light in a unique way, leaving behind patterns that can be read across unimaginable distances. Among those patterns, oxygen is one of the most distinctive. A sharp dip in the spectrum at certain wavelengths reveals its presence, even when the planet itself is too distant to see directly. This technique has already uncovered atmospheres rich in hydrogen, carbon dioxide, and methane, but oxygen remains the great prize. Finding it would be a moment of wonder, a sign that somewhere, perhaps hundreds of light years away, life may be at work. Yet oxygen alone is not enough. Scientists know that some geological processes, rare but possible, can produce small amounts of oxygen without biology. The key lies in context, in whether oxygen appears alongside other gases that point more clearly to living cycles. A mix of oxygen and methane, for example, would be difficult to explain without life constantly creating and consuming them together. If oxygen is a signature of life, it also raises another question. Could alien worlds face their own version of the Great Oxidation? Life, in its earliest forms, might begin with chemistries that do not rely on oxygen, just as it did on Earth. Over time, if photosynthesis or a similar process evolves, oxygen could begin to accumulate. To organisms unprepared for it, oxygen would be a poison, sweeping across the biosphere as a global catastrophe. On another planet billions of years away from us, microbial communities could even now be struggling through their own oxygen crisis, with extinction and survival shaping the course of evolution. The possibility is humbling. We look for oxygen as a sign of hope, yet its presence may also mark tragedy. It tells us not only that life may exist, but that life may have endured hardship, collapse, and transformation. The very molecule that draws our attention to alien skies may have brought entire ecosystems to their knees before allowing others to rise. The search for exoplanetary oxygen is also a mirror, reflecting our own fragility. When we ask whether another planet breathes, we are reminded of how precarious our own breath is, maintained by forests, oceans, and countless organisms. The line between flourishing and collapse is thin, and it has been crossed before. If oxygen is found elsewhere, it will not only hint at alien life, it will remind us that the story of survival and catastrophe may be universal, written again and again across the cosmos. In the glow of distant starlight, we search for worlds that breathe. We hope to find companions in the universe, not identical to us, but shaped by the same paradox of oxygen, balancing between gift and danger. And whether those worlds are thriving or still enduring their first oxygen catastrophe, their stories echo ours, linking the fates of planets across light years. The thought of alien worlds facing their own oxygen catastrophe draws us back to a truth that has played out on Earth again and again. Life is fragile, yet life is also stubborn. It clings to existence in places where survival seems impossible, enduring changes that wipe out the majority while leaving behind the few that adapt. From these survivors, new worlds of biology emerge. The Great Oxidation was not only a story of extinction, but also of resilience, and in its aftermath, we can trace lessons about what it means to endure. When oxygen first flooded the atmosphere, most of the biosphere collapsed. Anaerobes, which had ruled for billions of years, disappeared from the open seas and sunlit shallows. Yet they did not vanish entirely. They found safety underground, in sediments, in the depths of the oceans where oxygen could not reach. These refuges allowed them to persist, and many of their descendants are still alive today, hiding in soil, swamps, and deep beneath the crust. The lesson is clear. Even in global catastrophe, life finds pockets where it can wait for conditions to change. Other microbes did more than hide. They adapted. Some learned to detoxify oxygen with enzymes and antioxidants, protecting themselves against its corrosive chemistry. Others went further still, discovering ways to use oxygen as a tool. In these early experiments, life turned poison into power, laying the foundation for aerobic respiration and the rise of complex cells. What had once been a threat became the very thing that fueled growth and innovation. Adaptation is never instant. It is a slow, patient process written through countless generations. Mutations arise, some harmful, some neutral, and occasionally one that provides an edge in survival. In the harsh ages of the Great Oxidation, those rare advantages made all the difference. A microbe with a new enzyme could live where others perished. A cell that endured oxidative stress a little better could multiply while its neighbors failed. Over time, These small victories accumulated, and life as a whole shifted into new forms. We see the same lesson echoed in later extinctions. When the Permian apocalypse stripped away 9 out of 10 species, the survivors were those that could tolerate extremes of heat, drought, or low oxygen. When the asteroid struck at the end of the Cretaceous, ending the reign of the dinosaurs, small mammals and birds endured by adapting to new diets and hiding in sheltered environments. In every case, catastrophe cleared the stage, but survivors turned disaster into opportunity, expanding into niches left empty by those that could not adapt. The resilience of life is not limited to the grand scale of extinction events. It is written across the planet even now. Microbes thrive in boiling springs, under crushing pressures in the deep ocean, and in frozen deserts where almost nothing else can survive. Their presence in these extreme environments tells us that life does not merely cling to the edges, it transforms them into homes. Adaptation is not just about survival, it is about invention, the creation of new ways to live where none seemed possible. The Great Oxidation stands as perhaps the clearest example of this lesson. Oxygen was a catastrophe, but it became the foundation for forests, animals, and the complexity of the modern biosphere. Without the resilience of microbes that adapted to oxygen's challenges, there would be no multicellular life, no breath of humans or whales, no songs of birds in the trees. What began as near death became the greatest opportunity life has ever seized. These lessons remind us that survival is not about strength alone, it is about flexibility, the ability to bend without breaking, to shift when the environment changes. Catastrophes will always come, in one form or another, but life, again and again, has shown a quiet resilience, turning the harshest conditions into the seeds of new beginnings. And as the story of oxygen unfolds further, we see more clearly than ever that its gift is never simple, for even as it sustains, it also destroys, demanding vigilance and adaptation from every organism it touches. The story of survival in the wake of catastrophe reveals a truth that touches every living thing. Oxygen is both a gift and a curse. It is the gas that allowed life to rise into complexity, yet it is also the same element that corrodes, burns, and slowly tears at the fabric of cells. To live with oxygen is to accept this contradiction, to draw strength from a substance that is always waiting to cause harm. The gift of oxygen lies in its energy. By carrying it into their cells, organisms unlock vast reserves of power hidden in food molecules. Instead of scraping by on the meager returns of fermentation or other anaerobic pathways, oxygen users can release many times more energy from the same source. This energy fuels muscles, drives thought, and powers the delicate symphony of life. Without oxygen, the forests could not stretch skyward, animals could not grow large, and brains could not evolve the capacity for imagination and memory. The world of complexity depends upon oxygen's boundless generosity, but this same generosity is edged with danger. Oxygen's power comes from its hunger to bond with other elements, its tendency to react with almost everything it touches. Within cells, this reactivity is carefully managed, channeled through enzymes and pathways that guide it into safe and useful forms. Yet even with these safeguards, some of oxygen's energy escapes control. Free radicals form, molecules with unpaired electrons that lash out at DNA, proteins, and membranes. This is oxidative stress, a quiet but relentless process that gnaws at life from within. Every breath carries this duality. Oxygen flows into lungs, diffuses into blood, and seeps into trillions of cells, where mitochondria harness its potential. In that same moment, the risk of damage is also present, a price paid for power. Over years and decades, the effects accumulate. Wrinkles spread across skin, organs lose their sharpness, and memories falter, all shaped in part by oxygen's corrosive touch. Aging itself is intertwined with the very element that sustains us. Plants, too, wrestle with this paradox. While they release oxygen into the atmosphere through photosynthesis, they must also protect themselves from its side effects. Their cells are filled with antioxidants and repair systems that keep oxygen from unraveling their tissues. Fish in the sea, insects in the air, and microbes in soil all face the same challenge. To live in an oxygen-rich world is to walk a tightrope, balancing the benefits of energy against the harm of reactivity. Even ecosystems feel the weight of oxygen's contradictions. In times when its levels rose too high, the planet itself became volatile. Forests ignited more easily, and wildfires spread across continents. In times when oxygen dropped too low, animals struggled to breathe, and ecosystems collapsed. Life flourishes in the narrow middle ground, where oxygen is abundant enough to power complexity, but not so abundant that it tips into chaos. This balance is delicate, maintained by cycles of photosynthesis and respiration, by forests and oceans, by the endless breathing of the planet. It is a balance that has wavered across deep time but has never disappeared, carrying forward the contradiction that defines oxygen. To see oxygen as both gift and curse is to recognize how deeply it shapes every moment of existence. It is the element that makes movement, thought, and growth possible, but it is also the element that ensures nothing lasts forever. It sustains and it destroys. Life has endured by learning not to conquer oxygen, but to live with its duality, to embrace its power while enduring its harm. And in this paradox, the legacy of the Great Oxidation still echoes. Oxygen brought both devastation and possibility, and that tension continues to shape the earth today. Every forest, every ocean, and every breath carries the memory of this contradiction, a reminder that the same molecule that almost ended life also made us possible. The paradox of oxygen as both gift and curse becomes most striking when we consider its legacy. Every breath drawn today is tied to an ancient catastrophe, a chain of events that nearly erased life, yet ultimately made all of complex biology possible. The Great Oxidation was not just a moment in Earth's past. It is stitched into our very existence, a ghost that lingers in the air, whispering through the rhythm of every inhale and exhale. When cyanobacteria first released oxygen into their surroundings, they could not have foreseen the consequences. Entire ecosystems collapsed, oceans turned red with rust, and microbial kingdoms vanished. Yet in that devastation lay the seeds of possibility. Oxygen lingered, slowly filling the atmosphere until it became not a fleeting presence, but a permanent part of the planet. With it came the chance for cells to grow larger, to cooperate, and to specialize. Without that upheaval, the blueprint for complexity would never have been written. The very structure of our own bodies carries this inheritance. Our cells are powered by mitochondria, the descendants of ancient bacteria that first learned to tame oxygen. The energy coursing through our tissues is a direct continuation of the partnership that began billions of years ago, when one cell swallowed another and forged a bond strong enough to last to the present day. Each spark of thought, each beat of a heart, each stride of movement is fueled by the chemistry that emerged only because oxygen reshaped the earth. The Great Oxidation also left its imprint on the planet itself. The skies turned blue, the seas cleared, and the crust of the earth recorded the event in bands of iron, locked forever in stone. These geological layers are not just markers of destruction, They are the memorials of transformation, recording the moment when life altered the entire planet, and the planet, in turn, altered life. In this way, extinction became the pathway to abundance. The microbes that perished in oxygen's wake made room for new forms, and those that adapted gained an engine of power that fueled innovation. The forests of towering trees, the oceans teeming with fish, the flocks of birds that sweep across skies, all trace their origins back to this turning point. It is no exaggeration to say that every plant and animal is an echo of the Great Oxidation. Without it, Earth might still be cloaked in haze, its biosphere small, quiet, and microbial. Even our sense of time is marked by oxygen's legacy. For billions of years, evolution moved at a slower pace, limited by the energy available to single-celled organisms. After the Great Oxidation, the tempo shifted. Energy flowed more freely, complexity blossomed, and life began to explore possibilities that were once out of reach. In a sense, oxygen accelerated the story of the Earth, setting it on the path that would eventually lead to the rise of animals and the emergence of human beings. Every breath drawn today is a reminder of that history. The oxygen filling our lungs is the same element that once choked ancient seas and turned skies toxic. What was once catastrophe has become continuity, an unbroken cycle sustained by forests, oceans, and photosynthetic life. It is the air of survivors, passed down through countless generations, carrying forward the memory of a world that nearly ended and then began anew. The legacy of the Great Oxidation is therefore more than scientific curiosity. It is the foundation of our very presence on this planet. Catastrophe and creation were bound together in a single event, and the result is the living Earth we know today. From the rust-red rocks of ancient seas to the breath rising in our chests, its imprint is everywhere, shaping not only what life has been, but what it continues to become. And as we near the close of this story, the final reflections turn toward the breath itself, the moment when the Earth first filled its skies with life and death at once, and how that ancient breath still lingers in ours. The legacy of the Great Oxidation is not something locked in ancient rocks or confined to the distant past. It moves through us even now, in the steady rhythm of every breath. The air that fills our lungs is not new. It is part of a cycle that began billions of years ago when the first waves of oxygen escaped the seas and spread across the skies. Each inhale connects us to that moment, when the Earth took its first breath and nearly suffocated under its own creation. To live in this world is to breathe the air of survivors. The oxygen around us is the continuation of a story written by microbes that endured catastrophe and turned poison into power. Their resilience is carried in our cells, in the mitochondria that still burn oxygen to fuel every heartbeat, every thought, every step. We are living proof that out of devastation can come possibility, that from near death can rise astonishing life. Without the Great Oxidation, there would be no forests casting their shadows across valleys, no oceans alive with coral reefs and shoals of fish, no wings sweeping across the skies. There would be no humans, no stories, no memory. The catastrophe that once seemed like the end was in truth the beginning, the point where life stepped onto a path that led to complexity, diversity, and awareness. The air that destroyed worlds of microbes became the foundation for everything we know. The memory of that upheaval is still written across the planet. It is in the rusted seams of banded iron buried deep beneath the ground. It is in the blue of the sky, cleared long ago by oxygen's rise. It is in the fragile balance of forests and oceans that continue to renew the breath of the planet each day. And it is in us, carried in the oxygen coursing through blood, binding to hemoglobin, nourishing the body in a cycle that began with the first cells that learned to breathe. To think of this is to feel the strange intimacy of deep time. Billions of years ago, the skies were orange and the seas were green, and the earth seemed alien compared to today. Yet within that alien world, the foundations of our existence were being laid, molecule by molecule, breath by breath. The same atmosphere that now sustains us was forged in catastrophe, tempered in extinction, and steadied across eons of trial and change. Every breath is a memory. Each inhale carries the echo of cyanobacteria, releasing their oxygen into shallow seas, unaware of the transformation they were unleashing. Each exhale is a continuation of that cycle, proof that life not only survived the Great Oxidation, but also turned it into the most profound opportunity in the planet's history. The paradox of oxygen remains. It sustains and it corrodes. It creates and it destroys. Yet in this contradiction lies the story of resilience, the reason we are here, the thread that links us to the deepest past. We live in its gift, even as we carry its risks. We walk the narrow balance that life has always walked, between too much and too little, between suffocation and fire. And so, as we reflect on the Great Oxidation, we are reminded that life itself is fragile, but never powerless. The catastrophe that once threatened to erase the biosphere became the breath of the future. Out of extinction came possibility, and from that possibility came us. Every breath we take is not only air, it is survival, memory, and legacy, all entwined. It is the soft reminder of the day the earth first filled its skies with life and with death, the day the planet itself began to breathe.